Perfect, guys. So let's start talking about, I think there was a bond question that we haven't done. So let's do the bond question first, okay? This was from the last assignment. Let me see. Let me close this one here. Can you check your bond? One question. Here we go. Yeah. So why don't we do a program already so we can create and then we can modify as much as we want. Okay. So let's create one program, guys. Okay. As usual, remember, let's call it. Oh, sorry. Function. And let's call it my bond, something like that. We'll put my bond 1. Okay. First, without any data, let's create what we have. So what I have here is the information that I need to have to run this one here is the yield, right? I need to have the coupon rate. So that needs to be provided to me. And we have that in the question. Then we have the settlement. And then we have maturity. All right, guys, this is the data that we should have. Okay, so in our example, we have, let me copy this stuff here. In the question that we have at hand, guys, we have, I have that the yield equals 0.04, that the coupon rate equals 0.05, the settlement is, where's that, 17 June 2018. This is what they provide us, and maturity was equal to where do I see 18 December 2020. Do you agree? So this is the data that we have in the question, guys. So no questions, guys. No questions? Okay, so now the first question is, okay, provide me with the bond price. Okay, if we want to do the bond price, guys, let's call it bond price. Okay, this is going to be my variable. And the command is bond price, like this. It's not bond, it's BND price. And the information that we need is exactly this. We need the yield, the coupon rate, and the maturity. Okay, so we can have this one here as our output. So the bond price is going to be my program, and someone needs to provide me the yield, the coupon rate, the settlement, and the maturity. And I simply put this into my MATLAB command that is BNB price. And then we should have it. Okay, my second question is what? Payment dates. Okay, so this is the second question that we have. And then this is a very simple question, guys. So it says basically, let's call this pay dates. Okay, and there is a command that is called CF dates. This one here, cash flow dates. Wait. CF dates, and then what we need to enter, guys, is the is the settlement. Okay, so basically what this command is going to do is going to tell us when exactly we're going to be paying the coupons. Okay, so for that, I need a settlement when we started. I need to have the maturity. And there are a bunch of options here, guys. Now, for example, if I want monthly, this is going to be 12. But I think they say it's going to be quarterly. There are bases. So these three guys, I will type what I'm doing, okay? It's basically this what I'm doing. There's missing some more information, but indeed, this is what it means. The 4 means quarterly. The 3 basis is the actual, it uses the actual number of days in the calendar. And the one that I'm using is the end of the month rule. So basically the bonds coupon is going to be payment the last day of the month. All right, so we are learning here the CF dates. This is a cash flow dates. We need, when do we start the bond? When do we finish the bond? These are quarterly payments. This is the basis. It's going to be 365 days. And then we have end of the month. This is a common structure. As usual, guys, if you want to have more information about the CF dates, how this works, you simply go to help CF dates, and then you're going to have a bunch of things. Got it? What is the problem with these CF dates? As you're going to see in a minute, guys, is that this appears like Excel numbers. Remember, it will appear numbers. We're going to see in a minute. We don't want numbers. What we want is dates. Okay. So let's talk about then specific dates. How do I create this one? So let me create this one. And we are going to transform numbers into numbers that represent strings into, dates into strings. Okay. And what I need from here is pay dates. Exactly that. And that's all. So we should be, remember the D that I write here is simply to stop my program somewhere. Okay, so I want to export this one here also. So remember, if I want to export something else, I need to use now the bracket, correct? And I think this should work. So we save it. Yeah, my bond one is okay. Okay, guys, let's say 2 minutes to copy. I will stop the recording and you just remember me to restart. Yes, so what I was telling to you guys is let's do a brief review on bonds. You know, and remember that bonds have face value, or also called nominal value. It has a coupon rate. This is the percentage interest rate that they pay per period. Okay, then we have something that is called the settlement date. It's basically when do we start the bond, and then we have basically maturity. Got it? Now, this one here is used to compute the coupons. And this one here is used to compute the bond price. I think most of you have taken classes with me on bonds, right? It's a very quick review. And so basically, guys, a bond looks like this, you know? Okay, you are going to invest some money, let's assume $1,000. And then basically what you're going to have is 1, 2, 3, 4, 5, let's say 6 periods, okay? Imagine this is 6 months, 12 months, 18 months, 24, 30, and 36 months, okay? So this is what we have. And then imagine that we have a coupon rate. Let's assume a coupon rate. Let's assume, okay, it's 5% each 6 months. Got it? So this implies that if my face value, okay, my face value or nominal value, imagine is what? I started this one, okay? I will not put anything here. This is the price of this one here is the price of the bond. Where's my price? Oh, I'm missing here the price of the bond. Okay, the price of the bond is what we call P. The face value, imagine, is $1,000. Okay, so my coupon with this one here, my coupon should be equal to what? 5% of this one equals 50, right? So basically, this implies, guys, that we're going to be getting 50 per period. And then what happens at the end? At the end, you receive your 50, and then you're going to receive your principal. That is basically your face value that is equal to 1,000. Make sense? This is the structure of the bond. So the settlement date is going to be here. Maturity date is going to be here. When we use the 4 in the EBUs, in the MATLAB, remember, we use 4 for quarterly. You want to use 6 for every 6 months. Got it? And what we're trying to do is we're trying to compute what is this price here. Now, as you can imagine, guys, how do you get the price? Any ideas? How do you get the price of a bond?
Can't you discount
That's
all
it.
the cash flows that you expect to receive?
That's all. What you need to do is you simply need to discount every cash flow from the future to the present, right? That's all the exercise of bond pricing. Now, the only issue that is missing is what? Okay, when I discount, I need to have a discount rate, correct? So how the discount rate is called in bonds is simply called the yield to maturity, or simply the yield. Got it? And imagine that this one here is, if this one here is 5%, remember that one?
Mm-hmm.
If the yield to maturity equals the coupon rate, we have something that is called par value or par bond. What happens if the yield to maturity is larger than the coupon rate?
The price is lower than
Exactly.
par.
Exactly. So this is called a discount bond. And if the yield to maturity is smaller than the coupon rate, so we have a premium bond. Okay, so this is my maturity. And as you can, or we have seen in classes, guys, this is always true. Make sense? So what this exercise is doing is, first, compute this one here. And second, tell me exactly when are these dates. Okay, so that's what we want. I want to know exactly these dates. When in the month I will pay these coupons. Now, remember that the coupons are going to be slightly different, because some days we imagine, if we are saying the last day of the month, someday the last day of the month is Saturday. Okay, so we need to go into a Monday, something like that. Got it? So you have 2 additional days, but the next one has 1 day less, etc., etc., etc. In average, the 50 is going to be the same, but it changes slightly because of the day you're going to be paying. Question, guys? Let's save this one. No pins, bonds. Okay, questions? Is clear?
Yes.
Yes.
Okay, so let's go now into the program again. Here we go. So that's what we're doing. My bond price depends on the yield. Remember, this is the market price. The coupon rate is computed to compute the coupons. When do we start? When do we finish? And then we compute the payments using the CF dates. You know, is quarterly payments. And I want the last day of the month. And the issue with this one here, guys, as you're going to see, is that this appears numbers. So it's very difficult to understand what date is exactly that. And then we use this command, the date string that they are proposing now. The new version is proposing daytime. I haven't tested, so I will not test at this point. And that's all. So what I need is, I need to enter data, right? That's the way I have structured this one here. So I will say, oh, sorry, oops, I cannot run this one here. I want the yield to be 0.04, the coupon rate to be, where's my coupon rate? Right. 0.05. My settlement to be, I can copy the settlement from here. And I want to copy my maturity to be like that. Do you agree, guys?
Yes, but Professor, then are you still going to also include the pay dates in the square brackets, since we're only just trying to calculate the bond
Yeah,
price?
but you want to see the pay dates are numbers. They are useless. So instead of using pay dates, I prefer to use pay dates. That is a transformation of the pay dates. You're gonna see in a minute. Oh,
Okay.
sorry. Yeah, no. So let me call this one. Let me call this one different. Okay, pay days. You're gonna see pay days. Okay, so let's debug this program. Remember, how do we debug? If I want to stop somewhere, I simply click to the in the number and appears a red square, and this means that the program is going to run. So in order to run this program, so this is pay days, and remember the names here can be whatever you want, X and Y, whatever you want. It doesn't matter. Okay. Oh, I'm missing something. No, I'm not missing anything. Okay, you agree with me? So we can run this one. So I run, and you see it called the program. It entered the values in here. Remember also, guys, that the numbers here, they need to be in the correct answer. Right? The yield is first, the coupon rate is second, settled, and maturity. Okay, so here we can move up to here. You just do continue. And I have the bond price. Take a look to the bond price. My bond price, guys, is 102.3591. Why is this possible? Someone can explain me. How do we call this bond?
What was the original price of the bond?
100. Remember, the default in bonds is always 100.
Yeah.
Oh, yeah, I forgot that. Normally, the bond of a price is given in percentage. 102 means is 102% of the original price. So it's basically,
okay.
if we assume 100, it's 102.
Okay. Isn't this a premium because it's greater than 100?
Yes, it's a premium, exactly. And how do we get this one here? When we have a premium, how is the relationship between the coupon versus the yield?
The yield is less than the coupon.
Yeah,
right?
the yield, exactly. The yield is 4%, the coupon is 5%. So this makes perfect sense. So we have a discount, a premium bond. Perfect, makes sense? Okay, so we have my bond price easily computed. Now what we can do is basically, where's my, yeah, oh yeah, the pay dates. Take a look to what happened with the pay dates. Look, do you see the pay dates? These are numerical representations of dates, guys. If you do in Excel also, you can find this type of dates. You see, how do you read that? You have no idea when we're talking about exactly, right? So what we can do is we can do a bullet point here at the last, and then we can take a look to pay dates. You see that? Now it makes perfect sense. 18 June, 18 September, 18 December, 18 March, etc., etc., etc. Make sense to you guys? Let me.
Yes.
Have you been able to run your program? It runs. So now let me run this completely again.
Go up a bit again on your
Where?
on your script, your command window.
Oh, command window. The command window. Here we go.
Thank you.
Professor, could you please show your editor window?
Yeah, here we are. Ready, guys?
I'm ready. I was able to get the code to run.
Perfect.
Yeah, I just had one question. Can you
Yes.
actually go back to the whiteboard?
To the yeah. Okay, so let me stop and let me go into my here we go.
I just had a question about the graph at the bottom because I'm not really able to see it too clearly. So it says so that's describing when the price of the bond deviates, like it's a premium and a discount.
Yes, it's basically so. You know what, like in this example, when the yield to maturity was smaller than the coupon rate, we have a premium bond. So this implies that the price, where's my price? The premium means that the price is larger than the face value.
Okay.
Got it? This is what we had, 102, I think, versus 100. Do you agree? But now what is interesting is that, of course, if you keep the bond, if you buy the bond here and then you keep it up to maturity, this is what you want to be observing. Not as beautiful like this one here. You know, you have the market goes like that, crazy. But always you want to arrive to this point here. Always. Make sense to you? Or you want to do an example? Let's do one example. It's very simple to understand. So imagine, I need your calculators, guys, if you can help me, please. Oh, very well. Imagine, guys, that we have a bond that has been for some period already, okay? And then we just have 1, 2, and let's assume this is the last one. So let's assume this is 50, this is 50, and this is 1050. Okay, makes sense to you? So now my question is, what is the value of the bond here? What is the price here? So let's assume that my yield to maturity equals 4%. So remember, the coupon rate equals 5%, right? Agree? So that's why I have coupons like that. Okay, so now let's assume I want to compute my price. How do I compute the price here?
So you said that's where we discount to the present value.
Exactly. So it's going to be this 50 discounted by 1.04 plus the second 50 discounted by 1.04 squared plus my 1050 discounted by 1.04 cube. Right, guys? Correct?
Yes.
Can you help me? So let's do this period. I don't know. I will put this period k plus 1, k plus 2, k plus 3. Okay, and k plus 3 is my maturity. Can you help me with this one here? Then I want you to help me to compute. This is p at time k, p at time k plus 1. P at time k plus 2. And of course, what is going to be my p at time k plus 3? P at K plus 1 is going to be simply 50 over 1.04, because I'm going to be here, plus 1050 over 1.04 squared. Now, P K plus 2 is going to be simply 1050 discounted by 1.04. And what is going to be the value of P at time K plus 3? You tell me. We'll do the K plus 2. 1050 divided by 1.4. This is 1009.62. Someone can give me these values here. You help me.
Wait, sorry. So the red is K plus 1.
Yes. So so remember that if we are here, this 50 already disappeared. I only have this one and this one, correct? If I'm here, this 50 already disappears, so I only have this value. And then when I'm here, the 50 disappears also. What I'm left is with what? With $1,000, you agree? So imagine just in case I want to give you my bond today and matures today. Do you believe you're going to be willing to pay me more than 1,000 or less than 1,000? Do you think I will accept less than 1,000? It's impossible, right? Because today the value of the bond is 1,000. So what is the price of today bond? So here, I mean in K3, 1,000 for sure. This one here, I computed this one here is 1,018.86. I don't know this one. It's 50 divided by 1.4 plus 50 divided by 1.4 squared plus 1,050 divided by 1.04 power 3. Okay, so this is equal to 1,027.75. Do you see that? So this is what this means. Even though you start at a higher level, you're always going to end up in which value? This one here is a face value. Always. You can do the exercise if you start here. It's always going to happen. Of course, the graph is not as beautiful as this smooth line. It looks more like this. No, and how this changes because yield to maturity, guys, changes. So the market sentiment, the market valuation of a bond changes. Do you agree? Perhaps the Fed increases interest rate, perhaps the Fed decreases interest rate, perhaps there is something fantastic going on equity markets, perhaps something terrible in equity markets. Everything that can change the mood of the market basically changes the yield to maturity. And the yield to maturity is the discount rate that we use to price bonds.
Okay, I think I understand now. Thanks.
Perfect. No. And remember, this is more programming, but it's important to understand what we're doing. So and this is crucial. Questions, guys? Make sense to everyone?
Yes.
Okay, so let me stop and then go back to my program. Okay, so now there was part of the assignment, guys. I told you create. I will show one program, and then we analyze the program. Okay, and then hopefully you have done that. So, guys, I don't need to tell you to give me your assignments. I assume you're providing this to my email. Okay, what I do is I normally have one of my PhD students to review that. Okay, so let me check here. What is mine? So this is part of the last assignment, guys. Let's read. Now we need to create an M file, name my linear equation that can replace values in a linear equation y equals a plus bx. No, and we are going to provide a and b. So the user is going to provide the y-intercept and the slope. No, and also the x domain. So they're going to say the minimum, maximum of x, the maximum value of x. So this is going to be user inputted. And that's all. And then what we say is, okay, can you create a line? Okay, graph the line, and then do a best fit line, something like that. So we are saying, okay, let's use this one here, this value. So these are y observations. And I have I want to analyze this one here in the range of x between -3 and 8, assuming that a equals 6. So my y-intercept is 6, and my b equals -1. Got it? And then I tell you, do a subplot, do a plot, etc. And then tell me and create and call another program is going to be called test mean error to estimate the mean of the errors. Got it? So that's all. Do you have any questions about this one here? No? So, okay, let me show you. So let me show you one potential program. Okay, so simply description. Okay, so someone needs to input A, B, the minimum value of X, the maximum value of X, and a series of observations. Do you agree? And what I will return is the fitted value and the mean of the errors. Got it? So now, remember, if I want to have how do you call it? I want to have an X in a given domain. What I will do is I use linspace. Do you remember linspace, how this works? Guys, remember linspace?
It just creates values equally distanced apart, right?
Exactly. And then you start in a given value, what I call min X. I end in a given value of X. And how many observations? What I do is I want, as soon as I want to match these ones with my Y observations, with these Y observations. So I simply say, you know what, count the number of columns. I will have 1, 2, 3, 4, 5, 6, 7, 8, or 7 observations. 1, 3, 4, 5, 6, 7. 7 observations, basically. Then what I do is I simply create my Y. Remember, this is the equation of the line, correct? It's Y equals A plus BX. I have A is inputted, B is inputted, and X has been created here. So I have my fitted line. This is my equation line. Then what I'm doing is I'm plotting X and Y. I'm gridding on. Then I create another figure. So when do I create figure, guys? Why do I do this?
It's to create a new page where you're going to do a graph.
Exactly, and not delete this one here, correct? I want to keep this one here too. Perfect.
Yeah.
And then I do a subplot. So how this subplot is going to look like? How many subplots I will have? How many plots in a subplot I will have in this, according to this one here?
It will have 2, but it will be 2 rows and 1 column. So it'll be like one stacked on top of the other.
Yep, perfect. And this one means what?
You're in the first plot, so the top one.
Exactly. I mean, in the top plot, right? And then what I say is simply plot X and Y. So plot my X values and my fitted values. And then what I do is the same subplot in the second, so the bottom plot. Just want to show both of them. I plot X, Y. This R means what? Red. You agree? And X, Y observations with OB. So you're gonna see it's gonna be appear rounds, circles on top of that. Got it? And then what these guys are asking me also is, wait, I want to know what is the mean of my errors. So just for fun, what I've done here is I've created another program that is called test mean error that is going to be called by this program. So let me open this one here. Okay. And what the test mean error does, guys, is take a, where's mine? Let's see. Where is my, what was the name of this one? My linear equation, right? Yeah, so let me move this somewhere here. Here. So my linear equation, guys, and this is what we have done in last class, is gonna capture this value, and this value is going to be exported also. But remember, take a look, this value here, guys, is not computed in this program. It's called from this program. And the program that does the computations is basically something that I call test mean error. I need to provide the y, this is my y fitted, and this is my y observations. Got it? So if you go to the test mean error, you see I receive y, I receive the real y values. And then remember, the errors are simply my observations minus my fitted value. Got it? And then what I do is simply they're asking me for the mean error. So simply the mean of my errors and return the mean E. This mean E is going to come here, and this one here is going to be exported to the user. Make sense to you guys?
Yes.
Okay, so let's run this one here. I need to have the data first. A6B is -1. So let me create here. A equals 6, B equals -1. Then I have mean X equals -3. Max X equals 8. And then I have Y observed values of Y is going to be this one here.
You're missing an equal sign there by max 8.
You're completely right. Yep. Do you agree? And I will semicolon each of them, semicolon, just not to show them in my screen. I do need to show this in my screen, right? Okay, so I have all the values that I need now. And then what I do is I simply run this program, like this one. Right, guys? A, B, min X, min max of X and Y observations. Agree with me? So we can take a look to what we are doing. So let's put perhaps here a first stop. We can do another stop here, and then we can do another stop here. Okay, so we're ready. So we simply run. I have my linear space. Take a look. So 7 values from -3 to 8. What is -3 is the mean. 8 is the max value. How many observations do I have? I have 7 observations. It's 1 times 7. Then I simply compute my y. My y is going to be A is given, B is given, so X multiply this one here, and here we go with my line. You see? Okay, so now from here I do my plot. I can continue here. Where's my graph? Oh, here we go. This is my line, guys. Everyone agrees with that? Grids on implies all the grid in here, the grids here. Then I've created a figure. So this implies that I have created an empty figure that is here. And then I simply start computing my subplots. And take a look to my subplots. Here we go. This is my Y variable. This is the real data. And this is my Y, my fitted value. Of course, we're gonna work with OLS later, but you see that's the idea. It's my line and my fitted values and my real data. Do you like this equation, guys? Do you like this line?
It's a little like too steep.
Yeah, too steep, right? Yeah, perhaps we can start with, okay, so let me finish this one here. So what is the mean of E? Remember, mean of E, I have Y. I have the Y observations. And I'm telling my program, go to this program here, compute this one here, and return this value. Correct? And then if I do that, I'm done. Here we go. This is my mean error, guys, -1.2857. Now, do you think we can improve the model? First of all, questions. Have you done this, right? Something similar? Have you got something similar?
Yeah, Professor, can you go down to
Yeah.
the screen below?
Mm-hmm.
I just want to see if you can go up.
This one?
Okay, just here. Yeah, just wanted to see here. Okay, thank you.
Okay. Okay, so now let's take a look to the graph. Yeah, what we can do? So we can modify this one here because that's the best fit idea, right? What can I modify? Let's just play, just one example. What can I do to move my red line to be closer to this one here? Give me some values that we can use. It needs not to be precise, of course.
So you could change the value of B instead of it being -1 to make it like -0.7.
Okay, perfect. Yeah, let's take a look to what happens, right? So I don't want to be stopping this stuff. I can simply run everything. Okay, do you understand why we're doing that? Because apparently this is too steep, right? With a -0.7 is we're moving the slope to be a little less than this one here. Okay, so let's run. And let me see my new graph. Oopsie, is this my new graph?
Yes, it is your new graph.
Is my new graph is better than the previous one? I don't remember the previous one.
Yes, it's slightly, the observation points are slightly closer to the slope.
Yeah, okay, so let's exaggerate something to say something. Okay, let's do this -0.5 or 4. Okay, I'm just going to exaggerate to see the difference, guys, in the graphs. Yeah, I don't see this a lot.
Yeah,
I don't think you ran the program.
I'm not running the program, you're right.
I don't think you ran the new one.
Yeah, I'm not running the new one. So why I'm not running this one here? Yeah, I'm here. This is okay. Oh, of course I'm not running. Sorry, guys, this is only the definition of the variables. I need to run the program. You're completely right. Yeah, I need to run this stuff here. Yeah, this is terrible now. Do you see that? 2.87 versus 1.57. No. So let's go back to something less. And then with that, I stop because you're gonna find the technical way of doing this stuff. That is the ordinary least squares. Yeah, still this is worse than the previous one, right? I have an error 1.28 versus 2.03. Perhaps it's the slope also that we can change. Sorry, the y-intercept that we can change. So let's do one. Perhaps we can move this to be lower, right? V4, perhaps. No, 4 is too much. Perhaps to be 7. And that's interesting. I don't know. And with that, we stop. Oh, it's even terrible. Yeah, makes sense to you? The program makes sense to you? So you understand how this works and how you can be programming this stuff. Oh, you have
could
to
make A like 3. I think that's
yeah. Okay, so the last one, okay, just to move. Let's do A3. And let's run the program again. Oh yeah, we improve it, you see? We improve seriously. And then of course, what we can do later, guys, is and this is what you're gonna do later. Oh, not this one. No, this one. Where's my? Here we go. What we can do perhaps is a quadratic or something like that, because I have one value is outside here. But good. Makes sense to everyone? Guys, make sense to everyone?
yes, I understand.
Excellent, excellent. So now let me continue moving here. Okay, guys, so let's do some linear algebra, very quick linear algebra. We started already on that, but I need that for you to understand what is the Wallace model that we want to start programming. Okay, so do you remember how do I create an identity matrix? For example, I want to have an identity matrix, a 3x3 matrix. So let's call this X. How do I create an identity? Oh, let's call this I, caps I. I want to have a 3x3 identity matrix. What do we use?
Is it like the I command, but like
Yeah.
EYE?
Yeah, I. That's right. You can use either one because the die is going to be, or if you want, you do I33. Okay, perfect. Now, well, we have done matrix, we have done operations element by element, we have done all this stuff, right? So we need to go to more complex, not more complex, but okay, can we create a matrix A, guys? Let's do 1, 2, 3. Oh, yeah. You know what? Let's do 1 to 9. And I want you to transform this one here in a 3x3 using reshape. And let's call this A1. So I want this to be 1, 2, 3, down, 4, 5, 6, down, 7, 8, 9. Using the reshape command. Yeah, I can close this one. I can close this one. Close it. Ready? Okay, guys, you tell me. Reshape what?
A,
A?
and then it'll be a 3x3.
Yeah. Like that. Yeah, that's okay. Yeah, that's right. It does first this one here. It doesn't matter at this point. So remember, guys, that if you know this property, right? That if I multiply a matrix times identity matrix, what do you get?
You just get the same matrix back.
Exactly. Do you agree? So let's do that. A1 times I3. Right? That's what we're saying. Makes sense to you? Do you remember that? Okay, let's take a look to the determinant of a matrix, guys. So let's assume, in econometrics, there is a concept that is very important. It's what is called non-singular or singular matrix. Do you remember what is a singular matrix, guys? In terms of the determinant? A singular matrix means what, guys?
Was it that one had a determinant and one didn't, or something like that?
Yeah. So let me go back to my other screen. Let me move to this one here. Let me open a new one. Yeah. So remember, guys, what is crucial is so imagine. Do you remember this example I used? Always kind of similar example. Okay, how many equations do we have here? 2 equations, 2 unknowns. I should have a unique solution, right? Yes or no, guys?
Yes.
Yes. So remember that I can express this one here as a 3, 2, 6, 4 that multiplies x and y, and this is equal to 6 and 12, correct? So if I call this a, x equals b, indeed x is simply equal to a minus 1 times b. Correct? Guys?
Yes.
Yes, and what is interesting, guys, is that x, the a minus 1 is simply equal to the adjunct of a divided by the determinant of a times b. Okay, so this is the definition of a minus 1. So the determinant is crucial, guys, because if a is singular, this means that the determinant of a equals 0. And what happens if the determinant of a equals 0, guys? What happens here? Any number
Isn't it
divided
an
by 0.
infinite?
Yes,
mhm.
yes. So basically, this means that a minus 1 is undetermined. Do you agree? So basically, guys, there is no solution. There is not a unique solution. There can be millions or billions of infinite solutions to this system. Make sense? So that's why what we want in econometrics, what we want, well, in general, not only in econometrics, we want A to be non-singular. So this implies that the determinant should be different from 0. Got it? Now, let's take a look to A. A in my example equals 3, 2, 6, 4. If I find the determinant of A, remember it's going to be 3 times 4, 12 minus 6 times 2. So I get a 0. So this implies that A is singular, right? If A is singular, the inverse of this one here is what? Undetermined. Etc. Make sense to you?
Yes.
Yes.
Okay, so that's why it's crucial for us to understand the determinant. There are a lot of properties that you need to know, and I will show you it very quickly, okay? So let me save this as. Let me show you this again. You see my screen?
Yes.
Yes, we could see it.
Yeah. So let's find. Let's call the determinant. That's the command determinant of A. Where is A? A1. I will use A1. Yeah, because I have a linear combination somewhere. Okay. So this one here is a singular matrix. Do you agree, guys? Because the determinant is 0. Take a look to find A minus 1. A1. Well, we can do inverse of A1. You see that? And the thing is that it's telling you matrix is singular. Make sense, guys? Do you understand? So now let's find another A. Can we copy? Let's create a random A. So let's say 2, 1, 3. 2, 1, 3. Let's do 4, 5, 6. I just need to be sure that I'm not creating 7, 8, 9. Yes, because I changed the order here, so it will not be a singular matrix. Now, can we do the determinant of A? You see? Make sense? Also, guys, one thing that is really important is that the determinant of A is exactly the same as the determinant of A. What is this one here? This means what?
Transpose.
Exactly. There is one property that says that the determinant of A is exactly the same as the determinant of the transposal matrix. Take a look. Correct. There is another property, guys, that says, for example, if you shift one column or one row, you shift it, okay? Then what happens is that the determinant is going to simply change the sign, the sign. Let's do that. For example, let's do, yeah. Can we move this 158 to the first column? Let's create A1. What I want from A1, guys, you do this. I want the first column, sorry, the second column to be the first column. That's it. Do it as you want. Hey guys, how do we do that? Well, I can do brute force, right? I can do A, all rows, second column. I want this to be the first one. Next to this one, I want the first one, and next to this one, I want the third one. This is okay, right? Works or not?
Yes, that should work.
Yeah, it should work. You can do whatever. If you want, for example, you can do a flip left to right of the first element. So you can do, I will do another option. Okay, of course I cannot run this one here, but I can do, for example, flip left to right, A, everything, comma 1 to 2. And then I do A, everything, comma 3. Also should work, right? What I'm doing is I'm flipping left to right, all rows of column 1 and 2. So this is going to put row 2 at the beginning, row 1 second, and then I simply join with this one here. Makes sense to you guys? You need to play with this stuff, please. Okay, so I will use one of them. This is okay. This is more one. Got it? Now, can we find the determinant? Can we find the determinant, guys, of A1? You see, the magnitude doesn't change, but the sign changes. Now, guys, if you multiply one row or one column by a constant, the determinant is going to be multiplied by that constant. So why do we multiply the first row? Okay, so let's go back to A. This is A. Let's multiply the first row of A times 5. Let's call this A2. So the only thing that I want to multiply, the only thing that I want to multiply, guys, is the first row of A.
Wait, can you say that one more time? We're multiplying the
Yeah.
first row.
Just by 5, multiply it times 5.
Okay.
That's it, very simple. And then compute the determinant. Guys, ready? How do I do that? What do I do? Guys, come on, this should be very quickly already for you. So this should be, I want from A, the first column, the first row, all columns multiply by 5. You agree? Sorry. Yeah, what I will do is I will first I call this one here. And now what I want is for I'm sorry, I can copy this stuff. From A2, I told you the first one, I told you the first column, right? The first row.
Yeah, the first row.
I simply multiply this by this. You agree? So what I've done is well, you can do this in many different ways, but what I've done is I copied A and A2, and then I simply multiplied the first row times 5. This is the other one. I forget about this one. It's this one here. What I'm saying is A1, first row, all columns equals what is originally multiplied by 5. Got it? And then I have my vector here, my matrix here. Then can you compute the determinant of A2? Do you see that? Remember the determinant of A was minus 9. So it is multiplied 5 times minus 9. We obtain the minus 45. Right? And the last property that is useful is that normally, guys, imagine they multiply the complete matrix. Okay, can you multiply the complete matrix, guys? So this is A. Can you just call it A3? And I want A3 to be simply this matrix, all the matrix multiplied by 5. So this is going to be element by element multiplication, right? Ready? That's an easy one, right?
Yeah,
So-
it's just 5 dot star A.
Yes. So it's gonna be what? 8 times. 8
Oh.
times.
5, like dot
Exactly.
star.
Right. 8 dot star 5. And this is what we get. Everyone is with me? Guys, everyone is with me?
Yes.
Okay, so now let's compute the determinant of A3. Yeah, I have 1,000, this is 1,125, correct? So this number equals what? I will tell you in a minute. There is another command, guys, that is called the rank. So remember, the rank is simply the number of independent columns and rows, okay? So the rank of A3 is what? 3. Got it? So this implies that we have 3 independent vectors. And this should be because the determinant of this matrix is different from 0. So now, how do we arrive to this 1,125? Is simply the number that we have used to the rank, so the 3 times the determinant, times minus 9. You see? That's the one. So it's basically the number that has multiplied the complete rank, the complete matrix to the power of the rank of the matrix multiplied by the determinant. We use that for very rarely, but yeah, it's good to know. Okay, so now let's talk a little about the inverse of a matrix, guys. Let me check. Let's do where is my A again? The way you do the inverse of a matrix, guys, is simply inf of A, or you can do A to the, where is my power minus 1. They're exactly the same. So you can use inverse parentheses of A, or if you prefer, A to the minus 1. Now, what happens if you multiply A times A, or the inverse of A? What do we get here?
Should that be the identity matrix?
Yes. So this is more or less the equivalent, guys, to divide a number by itself. It gives you 1, right? This is more or less the equivalent of that. There is another property, guys, that says that the inverse of A, sorry, let me do the inverse of A transposed is equal to the inverse of A transposed. I cannot run this, so I'm just writing what is the property. This is a property, guys. The inverse of A transposed is equal to the inverse transposed. Right? So let's do that. So let me move this one here. Take a look. This is the inverse of A transpose. And this is, I first do the inverse and then I transpose. Oops. You see that? They are the same. Inverse of A transpose and inverse of A transposed.
Can you scroll back up to that formula for the rank?
Yes,
When you
yes.
multiply the whole
Rank. Oh, here we go. This one here. So this is equal. So the determinant of a matrix that has been multiplied by a constant is equal to the constant to the power of the rank multiplied by the original determinant. As you can see, the determinant here is exactly the same as the determinant here.
Okay, so just to confirm, just so I'm understanding sort of like the language of it. So the determinant isn't a part of the power, right? It's just a separate.
No. Yeah, no. Yeah, so
Okay.
let me write, perhaps I will copy this and we'll write this in a more elegant way. Just want to write. It's going to be 5 to the power of 3. Once you do that, times minus 9. Make sense?
Yes. All right. Thank you.
No problem. Okay, guys, so let's do something that is, let me open again. Do you see my screen, right? So we have done this already. Let's do this. This one here, guys, this part here is called system of equations. Do you understand what is this, right? This is a matrix times x equals a vector. Make sense to you? So the way you solve this one here is simply x equals a minus 1 times b. Agree with me? It's very simple. Now, in MATLAB also, guys, this can be done as a this way here. You obtain the same result. This is another way of finding the inverse in a much simpler way in MATLAB. So a minus 1b is going to be exactly equal to ab. Okay, so you do this, guys. Let's assume that I have 3x plus 2y equals 7 and x minus y equals 3. Okay, so what I want is you to tell me x equals what, y equals what, using MATLAB. So of course you need to define what is a, and you need to define what is b, right? And then x is going to be simply your formula is a minus 1 times b, or a, this one here, b. Okay, so let's do this in 3 minutes. Can you, let's do a function. Write a function. And let's call this my system. And then what you need to input is a and b. And then what you need to output is x. Very simple function, very, very simple function. Let's say 3 minutes, guys. I will stop. Perfect. So we're going to start creating my system 1, I call it. I need the input is simply a and b, and I will return x, correct? And basically, I can write here some comments. We'll say solves system equations. Agree? Ready? Okay, so basically that's it. If I have this information here, guys, I can provide x is going to be equal to inverse of a, sorry, times b. Correct?
Yes, that should work.
Yes.
And that should do it. It's very simple. Then we can complicate our lives and say, you know what, be sure that b is a, remember, this b should be a column vector, right? Sorry, a row vector. So we can transform that in a minute. But let's see if this works first like that. So what is going to be my a? So let's save. Yeah. Okay, so let's give a was equal to, according to my example, it was 3, 2, 1, minus 1, correct? And B was going to be equal to 7.3 transpose, correct, guys? And then I simply call this one here. Here we go. These are my values. Do you get these values? 2.6 and minus 0.4.
Can you scroll back up to A, please, just so I can see what those values were?
Yeah. 3, 2, 1 minus 1. Correct? It was 3x plus 2y equals 7. 3x plus 2y equals 7. And x minus y equals 3. Make sense?
Yes, I got it now.
Perfect. Okay, now how do we do, guys? Think a little. I want to be sure that B is always a row vector. So imagine what happens here if I made a mistake and I enter B like that. Okay, and I try to run this one here. Do you see that? It's gonna collapse because A is a 2 by 2 and B is going to be a 1 by 2. So there, it is not conformable. So what I want you guys is to ensure that B is always a row vector. So it's basically an n times 1, whatever. One minute. Some ideas here, guys. Well, what I'm looking here, guys, is the second dimension of B, right? The second dimension of B must be always equal to 1, correct, guys? If the second dimension of B is different from 1, what I need to do is simply transpose it. Okay, so what I can do is, remember, we have done if conditions already, so we can say if size of B, what, 1 or 2, guys?
So 2 for the column.
2, exactly. And not equal 1, then I need to do something, right? So I can say that B equals B transpose, and that's it. Should make it or not. And then we can complicate more stuff and do more controls in our program, but makes sense to you guys? So what I'm saying is if the number of columns is not equal to 1, simply transpose B to B prime, transpose it. Okay, so let's try. Remember, my B was defined like that. Now let's see if this works now. Now it works. Because let me stop here. Let me run this again. Take a look. A is okay, but B is a column vector. So what I'm saying is the size of B2 not equal to 1? This is going to be true, right? 1, true. Then transpose. And once you have transposed this one here, you are sure that you have now A is a square and B is a row vector. And then you can work with this stuff. Guys, questions? I can stop this. It's clear?
Yes, it's clear.
Perfect. So now, guys, what I want from you is just to, there is a Frobenius norm. Okay, the norm is simply distances between points, and the Frobenius is one of them. The sum of the squares of residuals, or the Euclidean, is one that simply says, I want to minimize the sum of the squares of residuals. There is another norm that basically is called the Frobenius. And what this one here is simply is the square root. Let me show you. Let me show you my screen. Where's my? Where is my what? Yeah. You see my screen?
Yes, we see it.
Okay. So now the Frobenius, guys, is basically the square root of the sum of the elements of the diagonal of x prime x. So this is called the Frobenius norm. Okay, the sum of the squares of the residuals, guys, is also called, well, is the Euler's model, right? We try to minimize the sum of squares of residuals, but there is another technique that is called the Frobenius norm that is simply try to minimize the sum of the diagonal of x times x prime. Do you remember what is this one here, guys? So let's assume something very simple. X equals 1, 2, 3, 4. Okay. So what happens if I do x prime x? Do you remember that? This is very famous, guys. In Euler's models, remember, the beta estimate equals x prime x to the minus 1 x prime y. This is the Euler's model. But what is this x times x? Remember what happened with elements on x prime x? What happened with elements in the main diagonal?
They're squared, so it's the variance.
Exactly. So this is going to be a square, and this is going to be a square number. Okay, these are simply numbers. It's not 0 squared. These square numbers. Got it? So basically, we'll try to minimize here is try to minimize the variances of a system. Got it? That's what I'm doing. When I multiply x times x, I got this matrix. I take the diagonal. Remember, diagonal only takes these elements here. Then I sum all these elements here, and then I take the square root of that. Right? Can you create that? Can you do this in MATLAB? So simply apply that formula. Let's use this example. A simple example. So we'll define, let's say it was x 1, 2, 3, 4. And then I can call this f is going to be equal to SQRT, square root of the sum of the diagonal of x prime x . No, it's not x. I need to multiply this one here. You agree with me, guys, or not? Guys, you agree? Guys,
I got like 5.4 or something like.
I know, let's take a look. Yeah, 5.472. Makes sense. Now in the in MATLAB, we have a command that is called the norm of X. And then we simply say for Frobenius is Fro. And correct. Okay, so perhaps we need to see something about eigenvalues also. So can we create a matrix, guys, that is going to be 1, 2, 3, 4, 5, 6. I just need to be here 7, 8. Let's do 0 just to be sure that we have this one here. So let's create this matrix again. And let's create B is going to be the eigenvalues of A. I will explain what is this and why these eigenvalues are so powerful, guys. Do you remember when we studied econometrics, guys? We have the when we did the vector error correction models, the Beck models. Well, if you have taken that, I'm not sure everyone took econometrics, but there are one model is called the Beck model, and the Beck model, guys, depends on the eigenvalues. Okay, just to determine if we have cointegration relationships. Basically, we use this concept of eigenvalues. Got it? But also it's very beautiful for the following. Take a look. Yeah, this is are you with me? This is a matrix, any matrix. Okay, just take the eigenvalues of the matrix. So you're going to have 3 elements, or they're ordered in a descending order. Now, do you remember how do you define the trace of a matrix? Let's call this trace of A. What is this 6? The trace, guys, of a matrix is simply the sum of all the elements of my main diagonal. 0 plus 5 plus 6 plus 1. Here is my 6. This is the trace of the matrix. Got it? Now, can you sum D? Oh, what I'm doing. Sum D. So what I'm summing is summing the eigenvalues. Take a look to what you get. This one here. Okay, so the sum of eigenvalues equals the trace of a matrix. The number of eigenvalues different from 0 equals the rank of the matrix. So what I'm saying is, okay, the rank. Just give me 1 second, guys. What is this part here? Okay, so the rank of a matrix, guys, let's call this R, is going to be equal to the number of eigenvalues different from 0. How do I find that? Is the number of eigenvalues different from 0? Okay, how do you do that? Can you do this condition here?
Wait, say that one more time. What are we trying to do?
Yeah, what I'm trying to do is I'm trying to show you that indeed the rank of a matrix equals the number of eigenvalues that are different from 0. So what I want from you is tell me, ask MATLAB to tell you how many values of these ones here are different from 0. You need to use some logical here, remember? Guys, at this point, your language should be very fluent. So you need to really remember the things that we have done in the past. So we're going to be using all of them.
So you said the rank is equal to the sum, the number of eigenvalues that are different from 0, right?
Yes, in this case, for example, it's 3, right?
Yeah.
Let's take a
So
look to the rank. Sorry, just to go directly. The rank of A is 3. So now show me that indeed the number of eigenvalues different from 0 equals the rank. How do I find that? Let's call this RR. How do I? Of course, I can count 1, 2, 3, but no. What I want from D, how many are different from 0? You tell me.
So what I did is I just did sum, and then
Yeah.
in the brackets I have D is not equal, so like the tildes and then the equal sign and then 0.
That's right. Because remember, what is this one here is a logic. It's going to provide me a zeros and ones, right? Of each value. So it's going to give me 1, 1, 1. If I sum, I get what I want. Perfect. Okay, you see, we have done this in the past, guys. So that's why I'm teaching you slowly, but building up. So you need to catch up, otherwise we're going to be lost in a space very quickly. Make sense to you? And now what is interesting, guys, is that the determinant equals the product of eigenvalues. So let's do product of D. This is the product. And compute the determinant of A. Okay. Make sense? So let me stop share. And let me go again into my. So up to now, guys, we have done, where's my mouse? Up to now, we have done this one here, that is important. This one here is very important. What is interesting is, is that the properties are sum of eigenvalues equals what? A trace of a matrix, right? B, number of eigenvalues different from 0 equals the rank of A. And Z, the product of eigenvalues equals what? The determinant of A. And there is another property, guys, that is really, really powerful. And you're going to see that. So if we have, let's call the eigenvalues are always related to eigenvectors. Okay, and how do we find the eigenvalues, guys? It's very simple. So you do B, D.
Sorry, Professor, we can't see your MATLAB screen. It's
Oh, no,
still
no.
on your...
You see my white screen when I write?
No, we
No.
see like your Word document. That's what
No.
we're seeing.
Yeah, no, let me show you. I'm writing in a different way. Yeah, take a look. You see now my wet screen?
Yes, we see it now.
Okay, so we have the eigenvalues, guys, and the eigenvalues are these ones here. The sum of eigenvalues equals a trace. The number of eigenvalues that are different from 0 equals the rank. And the product of eigenvalues equals the determinant of A, correct? This is what we have done. Now, what is very important, and from here you're going to see how powerful is this one here, is that the eigenvalues are always related to eigenvectors. Okay? How do we get the eigenvalues and eigenvectors? The eigenvectors, let's call them V, and the eigenvalues that we have found already is D. And the command is the same. EIJ eigenvalues of A. Can you run this one here? You're going to have V and D. And here, what is crucial is this property, guys. AB equals BD. Show me that this is true. So I have simply BD equals eigenvalue of A, correct? So these numbers here are the same numbers that we obtained before, but in a vector form. Where's this one? Here, 12, 0.3857. Here we are. Okay. What is crucial, guys, is this property that AV, so AV is going to be equal to BD. Okay, this property is crucial. Can you show that? Let's do AB. So it's basically A times B, correct? And now let's do BD, B times D. You see that?
Yes, very cool. Yeah.
So why this is extremely important? Let me go back to my where's my whiteboard? Are you with me? So you have shown this part here, correct?
Yes.
Okay, so what I will do is the following. AB equals BD. So if I want to eliminate the B, what I can do is AB, B minus 1, and just not to change the equation, I will do this B minus 1 at the end, correct? So a matrix multiplied by its inverse is identity, and identity multiplied by a vector is the same vector, or matrix, sorry. So A equals B, B minus 1. Do you agree? Everyone agrees with me?
Yes.
Yes. So now, why this is extremely useful in mathematics, guys? This really seriously, I think is one of the most revolutionary findings that someone did. Why? For the following. So what is equal A squared? When you want to do a matrix square, it's not a square in each element. Do you agree? It's a very complex mathematical procedure, really. When I was doing algebra, linear algebra, this was one exercise that take me at least 3 pages to solve. Okay. Now, if you see this trick here, you want to see how fast this works. So this implies this is BDB minus 1. Sorry, multiply by BDB minus 1. Do you agree? It's 2 times A squared. Now, if we operate this one here, this is going to be BDB minus 1 times BDB minus 1. Now, what is this one here? Identity matrix, right? It's like 1. So this can be simply B minus 1. So do you remember D is a diagonal matrix? Do you agree? Yes or not, guys? Remember the diagonal matrix is that you have number, and zeros outside. Do you remember that?
Yes.
Yes.
Okay, that's right. So now what happens when you multiply a diagonal matrix? The value, so imagine 2, 0, 0, 3 multiplied by 2, 0, 0, 3. The result of this one is going to be what? It's going to be 4, 0, 0, 9. Do you see that? 2 times 2, 2 times 0, 4. 0 times this, 0, 0, 0, 0 with 0, 0. 3 times 0, 3 times 3, 9. You get this one here. And this one here, guys, if this is D, this is D, this is equal to D squared. Yes or not? So what is interesting here is that A squared is going to be B, B squared, B minus 1. In general, guys, A to the n is going to be equal to B, B to the n, B to the minus 1. This is beautiful. When I discovered this one here, it was one happy day. Now also, n can be a negative number. So if you want A to the minus 1, this is going to be equal to B, B to the minus 1, B to the minus 1. Can you show me this? Can you first compute A to, let's compute A squared. Let's compute this one here, and let's compute this one here, and check with the inverse of A. Check, these two numbers should be exactly the same. Okay, let's say 2 minutes maximum. Oh no, I didn't record. It was not recording. Gosh. Wow. So we're doing the for loops now, and basically this tells MATLAB you start at 1 and then you finish at 10. And what I want is to create X is going to be created, and the position is going to be defined every time that I changes. And simply, if it's I equals 1, it's going to be X position 1 is going to be the sign of 1 times pi divided by 10. This can be whatever function here. Okay. So let's try to run. And you can see X is going to be a 1 times 10. And the values are going to be these ones here. So let me show you. These are the values. Make sense? Make sense, guys?
Yes.
Okay. So now what I will show you one program, and I will give you a couple of minutes to understand what this program does. So I think it's called MyTrans. MyTranspose, this one here. This is going to be part of your assignment also, guys. Let me go here. Okay, you have 3 minutes to understand this program. Okay. So what this program is doing, guys, is simply transposing a matrix. So imagine that your A equals 1, 2, 3, 4. Okay, so what I want from you is what is A prime? You see, is 1, 2, 3, and 4. So that's what is happening. So I want this program is doing that. I want you to understand the for loop. So you have a for loop, and then you have another for loop. Now, by definition, guys, the first for that is the inner loop. The inner loop is the one that executes first. Once you execute this inner loop, you go to the outer loop, and that's the way it works. Okay. Okay, let's think for a couple of minutes. I try to understand. And let's go and understand this part here. So what is this part here, guys, first of all? What this part here is defining is an empty matrix. And this empty matrix is going to be filled according to this notation here. Make sense to you? So what we're doing here is simply I'm saying, okay, tell me the number of rows, tell me the number of columns. And what is what is crucial for you guys is to understand what is a transpose. So let me stop sharing here and showing you my what is a transpose, and that's what is crucial. What is my, what? Oh. Yeah, so let me open a new one. Okay, so what is the transpose? Let's do my simple example. This is my A. This is 1, 2, 3, 4. Okay, guys. So I have n times m. This is number of rows. And this one here is number of columns. Agree? So when I say A transpose, you know that this is going to be 1, 2, 3, 4. Now, let me write this one here in terms of positions. This is position 1, 1. This is position 1, 2. This is position 2, 1. And this is position 2, 2. Correct, guys? When you transpose, what do you get? This is position 1, 1. This one is going to be position 1, 2. This one here is going to be position 2, 1. And this one is going to be position 2, 2. Agree with me or not? Now, how are these with this in terms of positions? They are shifted. The columns, sorry, the row. Let me delete this one. The row, guys, becomes the column. And the column becomes the row. Agree with me or not, guys?
Yes.
And that's exactly what we try to do here. When I do a loop like this one, when I say for I equal 1 to n is rows, remember? And then I say for j equal 1 to m, these are rows, these are columns. And then what I do here is something, then I do an n, and then I do an n. So what I'm doing here is, okay, xji, because remember, I'm changing this one here, is going to be equal to aij. You see the change here? This goes in the columns, this goes in the columns going to the row. Make sense? This is exactly what we're doing here. Now, how this works? Works in the following way. So I starts with 1, correct? Then we go to j. J is going to be 1. So the first one here is going to be, here I create a x position 1, 1 is going to be equal to a position 1, 1. Agree, guys? Then remember, what I do first is the inner loop. So j changes now to 2. A continues being at 1 because we haven't finished the inner loop. So here I'm going to have x of 2, 1 is going to be equal to a 1, 2. Yes or no? X 2, 1, this part here, 2, 1 is going to be equal to a 1, 2. Make sense? Once
Yes,
I
that
have,
makes sense.
yes, once I have finished the inner loop, guys, okay, there is no more, right? Because m equals 2. So then I get out. So I finish the inner loop, then I go to the outer loop. So now it was 1, now it goes to 2. So now I equals 2. And then I start again. I equals 2, j comes back to 1 again. J is going to be 1. So this implies that I have x of 1, 2, that is going to be equal to a of 2, 1. And when j equals 2, x of 2, 2 equals a of 2, 2. You see? Take a look. x1, 2. What is x1, 2? x1, 2 equals a2, 1. And 2, 2 equals 2, 2. And that's it. But what is crucial, guys, is that you understand these ones here execute first. And once these execute, you jump into the outer loop. And that's the way it works. Oh. Makes sense, guys? And that's exactly what this program is doing. So let me go back. to the program. So we can stop this here and let's run it. Oh, because I need to write this one here. And here we go. Take a look. My A equals 1, 2, 3, 4, and my X equals 1, 1, 3, 2, 4. Exactly what I wanted. You see, I can type it here. X, type I. You see, guys, works. Makes sense to you? Okay. So now I need to check something with you. Oops. Yeah, I can my transpose, my for loops. That's okay. So now let's go into guys, my bond. We have done my bond today. Okay, so now let's go into some theory, because that's what you need to do for your fourth exercise. So let me show you. Where's my screen? Function is my. Give me 1 second, guys. I want to see. Yeah, you have it. Okay, so yeah, let me do some theory first very quickly. Yeah, do you see my screen?
Yes, your whiteboard, right?
Yes, my whiteboard, exactly. Okay, guys, so what we are going to be doing, and I will provide you the code, so you're going to analyze and you're going to start working with them. I will provide you a code that is called my net present value. Okay, so this is going to be your function. But what is the my net present value does is basically computes the net present value. Got it? And remember, the net present value is what we do here is basically imagine that this is 100 or 1,000. Then you have 900 here, and then you have 1,500 here. Okay, for example. And then you have the opportunity cost. Everyone has taken this class with me, I'm pretty sure. We have done NPVs, right?
Yes, Prof.
Yes.
Yes, perfect. Okay, so basically what I want from you guys is to compute this program, with this data, and what I want is to compute the net present value. So the program should be able to, you enter this number, so you should enter minus 1,000, 900, 1,500, the opportunity cost, and then you should obtain this value here. Okay, so basically your program should do minus 1,000 plus 900 divided by 1.1 plus 1,500 divided by 1.1 squared. And then you obtain the value that you should obtain. That's all what it does. And I can enter a huge cash flow, whatever, but it should be able to compute the net present value. That's all. Make sense to you? Okay?
Yes.
Okay, so let me save this one here. Okay, so let me show you in MATLAB now. And let's try to go very quickly on over that, and you're gonna have the assignment to do that. And you need to improve a lot also. Open. It is my NPV. Okay, so you need to improve this program, guys. I provide you inside data. You should be able to import this data. You need to be able to do a bunch of things, okay? And these are going to be asked in the homework number 4. So let's do the logic here. I have my X, this is my data, this is my opportunity cost, so this is my cash flow. What I'm doing here is what? I'm simply finding, what is that? If n larger 1, and n larger than 1. Oh, yeah. So basically, if I create a matrix as a data, I need to tell the one that has entered the data, sorry, I accept only a vector. Got it? So because either m is 1 or n is 1. But if these two numbers are different from 1, so imagine it's a 2 by 2, I have an issue here, right? Because it's going to be larger than 1 and larger than 1, you have an issue. But if m equals 1 and n equals whatever number, this condition is not satisfied, so your model should be able to work with that, right? Then you have the int is simply that the length of x is simply giving me the maximum dimension. So if I enter the data in this case, it's going to be 3. Let me run this up to here. Yes, I can run this from here. So my int, guys, is going to be a 3. So I have 3 elements, 1, 2, 3. And then from here is where you need to start working with your for loop. Take a look. So what I'm doing is the following. I'm doing I is going to change from 1 to 3, correct? Because I have 3 elements in my vector, 1, 2, 3. Now, what I will do is the following. I ask if I equals 1, so I equals 1 is going to take auxiliary is simply taking the x position 1. So x position 1 is this minus 1000. So what I need to do is I need to do nothing, right? Guys, do you agree with me? Because I don't need to discount anything. Now, this is crucial. The way when you create an empty matrix, guys, I'm saving or not? Oh, yes, I'm saving, good. When you create this empty matrix, guys, in order to enter more values to this matrix, what you do is you copy this matrix, you take a look, aux equals aux. Semicolon implies that I will put the values that result here below the matrix that has been already created. So what I do is, for the first element, just keep the same element. So let me go here. Take a look. Take a look to aux. Aux, the first element is going to be minus 1000. Correct? So what I'm trying to do, guys, is I'm trying to create minus 1000, and I need to discount the future values. I need to discount 750 by 1.1 and 2500 by 1.1 squared. That's what I'm trying to do, correct? But the first one, I don't need to discount this by anything because this is my present value. Okay, so that's what I'm saying. For the first value, don't do anything, just keep that the same value. And so your aux is going to be simply this value, minus 1000. But what happens when I equals 2? For example, here is 2. What I will do is I have my x position 2. So my x position 2 is 750. I need to divide this 1 plus opportunity cost to the power I minus 1. Do you understand this one here? Because I, for now, it's 2. I don't want to be discounted by 2. I want to be discounted by 2 minus 1. It's 1. Okay, so let's do this. Let's run this one here. Take a look to the aux. Minus 1000, and the second element that was 750 discounted by 1.1 equals 681.8. And then finally, if you run everything, oh, wait. So what is my net present value? So let me run. So I have created all the discounted values, minus 1000. This 0.68818 is equal to 750 divided by 1.1. And this 2066 equals to the 2500 discounted 1.1 squared. Just take a look. 2500 divided by 1.1 to the power 2. You see, 261. This is what we have here. Now, once we have aux, guys, is simply what I need to do is I need to simply sum them. And then I have my net present value. Agree with me or not, guys? Here we go, 1747.9. Questions? Guys, make sense to you?
Yes, I understand it. Yep.
Perfect.
So just to confirm, that first negative 1,000 is like that first downward arrow in your diagram, right?
Exactly.
Okay.
Exactly. And that's why you don't need to discount for anything, because this is a previous year. Do you agree with me?
Yes, I understand.
Okay, so guys, for next class, when I will, or where is my, let me, so we're gonna have sorry, I need to find my, where's the, so what I will do is I will send this to you. I will send you the fourth assignment. You're gonna have this fourth assignment, guys. It is getting, you know, we have done everything, so you're gonna be able to do this stuff. Okay, here you have the function. You just copy this into MATLAB, and then you do what we are saying here. And then you need to write all the programs here. These OLS, guys, leave it for the weekend. This is going to be your weekend assignment. Got it? Make sense?
Yes.
Yes.
Okay, guys, perfect.
So wait, when
yes.
is that assignment due?
No, this is going to be for the next weekend, for the next Monday, sorry.
Oh,
But
okay.
better if you start working now, because it is accumulating. Do you see that? But everything is going to be done for next week.
Okay, so
Monday,
you're saying that last question, wait until after our next class to do the OLS question.
No, yeah, yes, you're right. You're right.
Oh, okay.
You're right. Okay, and but the thing is that if you can be moving on, actually all these assignment number 4, 5, and 6 are going to be coming in this week, tomorrow, sorry, on Wednesday. All of them are going to be due on next Monday. Got it? But I suggest you to be moving with this stuff. If you do assignment 4, if you do this up to tomorrow, you're going to see that you're going to remember what we have done, because most of that is simply things that we have covered in this class. Got it? But in any case, the assignments 4, the one that I will send today, plus 5 and 6 that we're going to work on Wednesday, are going to be all of them due on Monday, next Monday. Okay, guys?
Okay.
Perfect. So we stop here. Any questions, doubts? No?
Prof, I have a question. When are you available? If we have any other questions?
Yeah, just send me an email. You know, this is virtual. I normally, not sure if it will be tomorrow. Tomorrow I have very late time. But in any case, just send me a